NRD 15 talks about Pappus's theorem. We're not going to confirm Pappus's theorem. We're not going to prove it overall. We're just going to check that it works in one particular case. And here's what Pappus's theorem says, though. In any situation where you have, let's say, some line in the xy plane, and if you have some region entirely on one side of that line, and that's a little, for detail that has to be dealt with, but if you have some region like this, right, and let's call that D. If you were to take that region and rotate around, and that gives you some, some three-dimensional shape there, then the volume is equal to the area of D times the distance traveled by the centroid. So let me write that. So distance traveled by the centroid. So in other words, you're going to have to figure out where the centroid of that thing is and just compute, how far does that go? I'm going to call this distance here r bar, by the way. So this is just 2 pi r bar. Oh, there we go. Okay, so that's what Pappus's theorem says. It's a cool fact. It's kind of amazing. Roughly speaking, sort of the idea is that, well, we have, normally when you take volume and if you drag volume in some direction, well, that areas, when you drag them, trace out a volume, right? And you just multiply the area times the distance. The problem is that some little bits of area don't travel as far as you rotate them around than others do, right? So this one rotates around that much. This little piece of area travels a much greater distance. And so if you're going to multiply volume, if you get volume by multiplying area times some distance, well, what distance? All the points travel different distances. Answer, it's the distance traveled by the centroid. It's kind of a balance, kind of a compromise between the ones that don't travel very far and the ones that travel much further. Okay. So that's what the theorem says. Now we're going to check that in this one case where we're using the y-axis as our line. So let's see here. So D is some region sitting over here where x is greater than 0. So here's some weird region. Call that D. And we want to write down, so first, write down a double integral that represents the volume that you get when you rotate this around the y-axis. So we're going to look at little pieces of area. And by the way, the earlier problems in this section kind of built up to this, right? So you're going to take little pieces of area, dA, and each one of those rotates around to make a little piece of volume that we'll call dV. And I claim that the volume, we're going to do a double integral. We're going to add up all these little pieces of volume, and in particular, each piece of volume is going to be 2 pi r dA, because that's sort of the distance we dragged it, and that's the area that got dragged that distance. So there you go. There's one more little step. I claim you can actually write down what that r is, because we've chosen a particular line to rotate around. We're rotating around the y-axis. And so that r distance is just x. That's because in this special case we're rotating around the y-axis. And so that distance is the same as x. Does that make sense? Are you good so far? Okay, so I claim that's x. How's everybody else? Does that make sense? Okay, so that's part one of this problem. So double integral representing the volume. Yeah, right. Okay, no, it didn't say compute. Right? So we couldn't possibly compute because we don't know what this domain is. There's no way that we could turn this double integral into a nested integral because I don't know what that shape is. So let's do part 2 now. Part 2 says, let's compare this with the formula for x bar and show that this confirms the theorem of Pappus. So the formula for x bar that's on this previous page here, here it is, x bar is that. So 1 over m integral x. Now, we're assuming the density is equal to 1. So it's 1 over m integral x dA. Of course, the mass is just the area when the density is equal to 1. So it's really 1 over the area times integral x dA. So we get 1 over a integral x dA. That's x bar. Okay. So I've got two things. I've got the volume is this. I've got the x bar is that. And notice that both of these integrals, the integral for v and the integral for x bar, they have a lot in common. This has got it's got some constants or whatever, but we've got volume is some constants times integral x dA. And x bar, integral x dA. They're very, very similar. They're just different constants. So we can relate them in a variety of different ways. So one thing I could do is I could say, well, from part 1, I know that integral x dA, if I look at this part 1 here, integral x dA is going to be v over 2 pi. And on the other hand, from part 2, I know that integral x dA is equal to x bar a. Right, so that's just looking at this formula. So this gives me that, and that gives me, that gives me that. So therefore, since these are, of course, exactly the same thing, that means that these are equal, and so I get v over 2 pi is equal to x bar a, and therefore v is equal to 2 pi x bar a. And now let's make it interpretate. What is x bar? Well, in our original picture, x bar is the x coordinate of the centroid. X bar is that distance. It's the distance from the centroid to the line that we're rotating around. So x bar is r bar. So v is 2 pi r bar times a, and that's what Pappus's theorem would say. Does that make sense?
Can you see it downloaded?
Yeah, sure. Like that? Yeah. So now this is not a general proof of Pappus's theorem. All this does is show that if you're rotating around the y-axis, then Pappus's theorem works. But it's a pretty good plausibility argument, and I claim that proving Pappus's theorem in general is not that different from what we just did here. Yeah.
Can we do 5.5?
Yeah. Is everybody okay with this problem
Sorry.
first? Yeah. No worries. Is everybody good? Okay. All right. By the way, there's lots of instances where Pappus's theorem is super, super convenient to use because sometimes, let me just talk about Pappus's theorem for just a quick second. Sometimes you might want to compute volume, and the volume might be a pretty tough problem. It might be like really not obvious what the volume is, but maybe R bar is like really, really obvious. Or sometimes it might be the other way around. Maybe you don't know what R bar is, the distance from the centroid. Where's the centroid? I have no idea, but maybe the rotated volume might be obvious. And that's what happens in problem 16 here. Maybe I'll just leave that for the moment. Here's an application going the other way. I put this on an exam one time, by the way. It wasn't here at Duke, but it was elsewhere. But I put a problem where you take this diamond, where it was at those points. So you take this little diamond shape, and rotate that around. Then I forgot what line I picked. I think we were rotating out around the line x equals like 3 or something. And you take that and rotate it around, and it gives you some, some shape kind of like that. And the problem was to compute the volume of that sort of like diamond donut, as it were. And the answer was, now you could do this with, slices, taking, triple integrals for volumes, and you could make that work. It's kind of inconvenient, but you can do that. But look how easy it is with Pappus's theorem. The centroid is obviously at the origin. So that means that our R bar is obviously 3. So the volume is 2 pi times 3 times the area of this diamond, which is also really easy to compute. That area is just 2. And so, boom, arithmetic, done. No triple integrals. So I thought that was a neat application. And exercise 16 gives a sort of a backwards, an application where instead of using R bar to compute V, problem 16, you'll use V to compute R bar. Okay. All right. Let me stop this recording here.